In this lesson, we are going to work on adding, subtracting, and multiplying radicals. So let's start by thinking about adding and subtracting with variables. So how do we simplify 5x plus 3x? Well, from our experience, we can add those because those are like terms, right? Now, the whole reason we can do that is because of factoring. We usually don't write this out, but what's really going on here is we're factoring out an x. These two terms here both have an x, so we could pull that x out. And 5 plus 3 is 8, so this is 8x. That's what's going on because they both have that same thing. Well, what if we have 5 times the square root of 2 plus 3 times the square root of 2? Well, we don't know what the square root of 2 is exactly. So this acts kind of like the x, right? So we could factor out that square root of 2. And 5 plus 3 is 8. So this is 8 square roots of 2. So here, the square root of 2, it's a number. It's about 1.414. I don't know exactly what it is, but I have 5 of them and 3 of them. Now I have 8. Okay, so we can add those. How about these here, all right? Can we add these? Well, we got the cube root of 17. I sure don't know what the cube root of 17 is there, but I know that whatever it is, I have 5 of those minus 3 of those. So here we can combine these, and that's going to give us 2 times whatever the cube root of 17 is. And then we've got this 4, and that cannot be combined because it doesn't have a square root of 17. All right? So we have 4 plus 2 times the cube root of 17. So what really just happened? Well, we just kind of see how when we're simplifying radical expressions, we can only add or subtract like radicals, okay? Just like we have like terms when we have variables, when we have terms that have the same radical and then we can combine them, all right? But they have to have the same radical, all right? So think of it kind of like a variable, or think of it as something we don't exactly know what it's worth, but we know here, for example, we got the square root of 3 and the square root of 3. They're both square root of 3. I have 4 of them, and we subtract 7 of them. Well, 4 minus 7 is negative 3. Negative 3 square roots of 3. So we can combine those because they're both the square root of 3. How about this one? Well, careful, they look the same, but this one is the cube root of 5. This is the cube root of 5. Again, don't know what the cube root of 5 is, but I know I have 5 of them, and I'm going to add 7 of them. So that's going to give me 12 cube roots of 5. And we've got this minus 3 times the square root of 5. That's different. The square root of 5 is a different number than the cube root of 5, so you can't combine those. All right, so that would be the idea there. Only combining like radicals. What about this? Which ones can we combine? Well, combine the like radicals. We've got 3 square root of 2 plus, how many square roots of 2 is this? Well, it's 1. So this is 4 square root of 2. And then we have 7 square root of 3 minus 12 square root of 3. And so that's going to be a negative, like that, negative 5 square root of 3. We can't combine those because these are square roots of 2, these are square roots of 3, like apples and oranges, or like x's and y's. You cannot combine those. We just leave it as one expression there. Okay? Okay, what if we have some variables and some radicals? Well, notice here we got y square root of 2. Do we have any other y square roots of 2? We do. So we have 3 y square roots of 2, and we have 1 of them. So altogether we have 4. We have 4 y square roots of 2. How about square roots of 3? Well, we have x squared of 3, and then we have x squared of 3, and we got 1 of them there. The coefficient is 1. Remember that word, coefficient, is the number in front. Here the coefficient is 3. Here the coefficient is negative 1, and that is plus 2. Because 3 minus 1 is 2. and they'd be x squared root of 3. So x squared root of 3 is kind of like the last name of it, okay? So these belong to the same family. They belong to the x squared root of 3 family. Okay, so we got to have the same radical, and if we're talking about variables and radicals, they got to be the same, okay? So when we're adding and subtracting, that's the key, all right? Now, what if they don't look like they're the same? Well, if the radicals are not alike, try simplifying the radicals first. So here, can we add these together? Now be very careful. This is absolutely not equal to the square root of 10. That is no good. You can't do that. Don't do it. That's the radical product rule, okay? The radical product rule says we can multiply them, but we're not multiplying, we're adding here. So we have to have like radicals. So what we need to do is we need to simplify this. How do we simplify the square root of 8? Well, the square root of 8 is the square root of 4 times the square root of 2, which is 2 square root of 2. Okay, so we remember when we're simplifying, we look for a perfect square that multiplies into 8, and it's 4. We can simplify this part, so we have part that we can simplify, part that we can't. But notice now they're both the square root of 2, or they're both terms of the square root of 2. So now we can add those. There's an invisible 1 here. So this is 1 square root of 2 plus 2 square root of 2. That equals 3 square roots of 2. Okay? That's the idea. So it didn't look like they were the same, but they end up being the same there. Okay? Now let me pause for a second here. You might be wondering, okay, so what's the point? Okay, well, the point, we can kind of see the point because here we have 2 radicals and here we have 1. All right? And just to verify this for ourselves here, if we take the square root of 2 plus the square root of 8, there it is, 4.24, something like that. And 3 times the square root of 2 is the same thing there, all right? So that's the idea there. We get the same value, but this is exact. That decimal number 4.24, whatever it was, is not exact. All right, how about these guys? Well, we got to simplify it. Remember, when we're simplifying, we're going to look for a perfect square that goes into that number. Is there a perfect square that goes into 12? There is. It's 4. Okay, our perfect squares are 4, 9, 25, 36, so on and so forth. Okay, we'll clean that one up in just a second. Let's simplify the square root of 75. Well, that's 25, which is a perfect square, times 3. Okay, now by the way, you can use the prime factor method here. That's totally fine. But in most cases, we don't need the prime factor method unless these numbers are really big. So get to know your perfect squares, and we can simplify the part that we can and the part that we can't. So here we can simplify the square root of 4. We can't simplify the square root of 3. We can simplify the square root of 25. We can't simplify the square root of 3. So we have 2 square roots of 3 and 5 square roots of 3. Add them up, and that equals 7 square roots of 3. Okay? So 7 square root of 3. So this means 7 times the square root of 3, but you hear how I'm saying it? This is 7 square roots of 3. We have 7 of this thing. So this becomes a constant. It is a constant, of course. Okay, but it's like a standard measurement almost. Okay? Kind of like when we say dollars. You have $7. Well, what is a dollar worth? Well, kind of depends on inflation, but that's the idea. Okay, so it's a constant amount. All right, how about this? Well, we've got this 3 hanging out here. And so we're going to simplify this, but this 3 is just going to kind of come along for the ride. So I'm just going to kind of write that out there. Let's break up the square root of 32. Is there a perfect square that goes into 32? Think through it. Does 4 go into 32? Yes. Does 9? Nope. Does 16? Yes. So find the largest perfect square. It's 16 times 2. All right. And so then that'll be 3 times, well, the square root of 16 is 4. Okay. And 3 times 4, this is all multiplied here. 3 times 4 is 12. All right. Now, we got to deal with this other one here, 5. Got to simplify the square root of 18. What perfect square goes into 18? 1, 4, 9, 16, 25. Which one? Well, 9 is the perfect square. 9 times 2. And the square root of 9, this is all multiplied. Square root of 9 is 3. And so 5 times 3 is 15. And we notice that we're just left with the square root of 2. Okay, so we have 12 square roots of 2 minus 15 square root of 2. So this equals negative 3 square root of 2. Again, the square root of 2 is our constant there. Okay. All right, and that's how we simplify that there. Okay. How about one more? What if we have the variable in the mix there? Well, again, the 6 is going to come along for the ride. Here, what perfect square is hiding in there? Well, there's a square root of 4. 12 is 4 times 3. And that x is just going to kind of stay in the radical. We can't clean it up. 7 is going to just kind of stick around, breaking it into what we can square root and what we can't. We can't square root x. If it was x squared, we could, but it's not. Is there a perfect square that goes into 27? There is. It's 9. 9 times 3. This is all multiplied. Okay, well, let's do a little cleanup here. In the first term here, I've got 6. The square root of 4 is 2. And then we got that square root of 3x. Here, 9 is 3, and we got the square root of 3x. We just kind of slowly clean it up. 6 times 2 is 12 times that square root of 3x. 7 times 3 is 21. And we notice that we have the same radical there. Okay, so that can be 12 minus 21 would be negative 9 times the square root of 3x. Since they both have the square root of 3x, that's our common, our like radical, and that just stays the same. And the coefficients simplify. All right, so that's the key. You have to make sure you got like radicals first, and then you can simplify by adding or subtracting. What about cube roots? Well, that's the same there. Okay, these act the same. So we're going to have the 3 is going to hang out. And then we ask ourselves, is there a perfect cube that goes into 24? There is a perfect cube that's 8. All right, 8 is a perfect cube because 2 to the third power is 8. All right. How about into 81? Is there a perfect cube that goes into 81? There is. It's 27. 27 times 3 is 81. All right, now that's kind of large. If you'd like to simplify that out, you might want to rewrite 81. You can do the prime factorization. 81 is 9 times 9, which is 3 times 3 times 3 times 3. So this is 3 to the 4th, and so you can kind of see that there is 3 to the 3rd hiding in there. Okay. That 3 to the 3rd is 27. So the cube root of 27 is 3. So this is 5 times 3 times the cube root of 3. This is 3 times 2. The cube root of 8 is 2 times the cube root of 3, which we don't know. That gives us 6 cube roots of 3 minus 15 cube roots of 3. And 6 minus 15 is negative 9 cube roots of 3. That's it. Okay. So cube roots are going to behave the same there. All these expressions are equal. Okay. All right. One more here. All right. Now we've got some variables in the mix here. We're hoping are hoping that these radicals will simplify to be like radicals. All right, that way we can combine it. So the 5 is going to just hang out. And this is a cube root. We can't really simplify that at all. Okay. Why not? Well, because the powers are not bigger than this index. Okay, x squared, cube root of x squared. You can't simplify that. If this was bigger than 3, we could, but we can't. Now here we can simplify some of this. Let's try that. So we got some cube roots. Well, we can cube root 27 can be cube rooted. And we can simplify x to the 3rd power. Okay. And we can simplify y to the 3rd power. Those are things we can simplify. We'll do that in a minute. And the leftovers are y, whoops, let's go x squared and a y to the 1st. All right, so remember here, we're multiplying these. X to the 3rd times x squared is x to the 5th. 3 plus 2 is 5. Y to the 3rd times y to the 1st is y to the 4th. Add the exponent. There's an invisible 1 there. We can clean this up. Let's go ahead and do that right now. The cube root of 27 is 3. The cube root of x to the 3rd is x. Cube root of y to the 3rd is y. And then we have this little cube root left over. Now, this one's a little different. We're actually stuck. Yes, we have these like radicals, okay, but can we add 5 and 3xy together? We can't really. So that was some nice simplifying, but we're stuck there. We can't combine them because we can't add these coefficients together because of that xy. So, all right. Well, that's adding. Next, we're going to go on to some multiplying and see how we can simplify with multiplying.